Okay, so let's start. So what are we doing? So what we're doing is we've reached almost to the end of chapter 6 on confidence intervals. So just as a kind of, just to remind you basically that for this week what we're doing is we're going to finish these main lecture notes. There's only 7 chapters. And then after that, which is going to be this week, the next week what we're going to do is to have a look at these some additional lecture notes which are kind of provide some extensions and clarifications for what we've done so far, but in essence will be kind of non-examinable. And then the week after we'll be going through some exam practice. Basically we'll look at last year's exam and some other questions which will kind of give you some idea of what you have to do for your exam in I think it's May or April, I forget which, and that's it. So basically we've only got 3 weeks left. And so what we were studying last week was the notion of constructing a confidence interval for population parameters. So the idea was that in most contexts we would obtain a random sample from a population, that is a collection of variables, random variables x1 up to xn, assumed to be IID, independent identically distributed, so basically independent copies of the associated population. And associated to this distribution would be generally unknown parameters such as the mean or variance of the associated probability distribution. In most cases these sampling distributions are Gaussian. And then the idea is on the basis of these observations we want to 1, estimate the associated parameters, for example, the mean or the variance, and then 2, to obtain an associated interval estimate associated to this estimate, in fact. So the notion was that what we were doing basically for most of last week was constructing a statistic associated to the random sample and the unknown parameter, and then basically determining those values of the associated statistic for which the parameter, the probability that the parameter lies in this interval is sufficiently high. Okay, and then that was essentially that was the idea. So again, you have a sequence of data, you determine a statistic for which you know the distribution of this data, and then basically you invert that the statistic to be a function of the parameter such that the probability that the parameter lies in a given interval is sufficiently high. Okay, IAR, level of confidence. So basically this is going to be another statement of that. So this is the case. So we looked at a lot of cases. So the notion in this particular case is you have a confidence interval for the ratio of 2 variances of Gaussian populations with unknown means. So the idea is this. Okay, we have a sequence of random variables x1 up to xn. They are IID, and they have mean, which are Gaussian, with mean mu1 and variance sigma squared 1. N1 is a sample size. Mu1 and sigma squared 1 are both unknown. Okay, independently. So there's a missing word here. So this statement is independent of this one. So now I have a collection, again another collection of IID random variables, in this case n2 of them, which are Gaussian, where the mean and the variance is different, and I don't know both of these means and variances. And what I want to do in this part of the lecture notes is to construct, I haven't got a pen here anyway, to construct a confidence interval for the associated parameter, in this case the ratio of the variances. And I'm under the assumption that I don't know the means. Okay, so the idea is what we want to do is to construct a statistic associated to the 2 samples x1 up to xn, which are functions explicitly of sigma squared 1 and sigma squared 2, functions of the ratio, if we want to construct a confidence interval for this quantity. And this is not particularly difficult because we know a lot of things. So we know, if you look back in the previous chapter, that if you take the sample variance S1 squared and scale it by the number of data points, okay, so I'm talking about this quantity here, which is this quantity here. So if I scale this by n1 minus 1, the number of data points, and divide by through the same variance, then this is chi square on n minus 1 degrees of freedom. Okay, because basically this thing, so this thing, scaled and by n minus 1 over sigma squared 1 chi-square n1 minus 1 degrees of freedom, and independently, precisely because the two collections of random variables are precisely independent, then using essentially the same result, except in the context of the y's, you have a chi-square on n2 minus 1 degrees of freedom. So this one, just basically using the results in the previous part of the lecture course. So remember, we have this assumption. Okay. Right, so now what do we know? Well, we know that the ratio of chi-squares divided by this degree of freedom, which are independent, give us an F distribution. So that is to say that if I look at this statistic capital F, now I take the ratio. So this one's chi-squared on n1 minus 1. This is the degrees of freedom, n minus 1, so I divide by that. And similarly, independently, this is chi-squared on n2 minus 1, so I divide by n2 minus 1. Okay, so obviously in this numerator, this factor cancels, and in the denominator, this factor cancels. So this statistic F is precisely S1 squared over sigma squared 1 times divided by S2 squared over sigma 2 squared. And by definition, this thing over this thing is precisely F distributed on n1 minus 1 and n2 minus 1 degrees of freedom. Okay, and remember, that's basically the idea. So we find a function of the data and of this unknown random variable, unknown parameter, for which we know the underlying distribution of the associated statistic, i.e. this is what's called a pivot, as I said last week. And then basically the idea now is to invert the pivot as a function of the parameters for which we're interested in making or constructing a confidence interval for. Okay, so the idea here is now that we know that the probability that this statistic, which lies between these two edge points, is exactly 1 minus alpha. So I don't have a pen that have taken them away for some reason. But basically these values, remember what these things mean. Okay, so I will just try and here. So for example, if I take this one, f n1 minus 1, n1 minus 2, to this one here, okay, which is appearing in this upper limit, then if you take a random variable which is f distributed on n1 minus 1 degrees of freedom and n2 minus 1 degrees of freedom, the probability that this random variable exceeds this value here, so there's a little bit of confusing notation. These are basically constants, these are the quantiles. In this case, this is a random variable, so the probability that I exceed this point is alpha over 2. Okay, so basically, because of the fact that this statistic has this distribution, the probability that you lie in this interval where I've just interpreted these two quantiles for you is exactly 1 minus alpha. And now we proceed upon our task of inverting that statistic, that is rearranging this probability as a function of the ratio of the variances precisely so that we can construct a confidence interval for this ratio of variances. Okay. And that's what's done here. So basically all you have to do, so you have sigma 1 squared over sigma 2 squared, so you basically, you want sigma 1 squared over sigma 2 squared, so you have to do 1 over this, and then you multiply by s1 squared over s2 squared on both sides. And that's what we've done here. Okay. So the thing is you take the reciprocal, which obviously flips the inequalities. That's why you have this one here, and the 1 over values are coming from the fact that you've had to compute the reciprocals. Okay, and so that's the confidence interval for the ratio of the variances for Gaussian populations for when you do not know the means. Okay, so this is the lower value and this is the upper value where these quantile values have been interpreted already. Okay, and if you want to compute okay, so that's basically what I just said here. So this is the summary of what I said here. And remember that we know something about the relationship between these. So remember the F distribution has 2 degrees of freedom. So for any given level of alpha, the value of alpha, there are a lot of values for different degrees of freedom. So basically the tables for these things are very sparse. So that we know that there's a relationship between these quantile values. So we know this thing. We're going to verify this formula here, actually. Okay, we actually already did that when we started to talk about the F distribution in chapter 5. Okay. So that's the confidence interval, the 101 minus alpha percentage confidence interval for the ratio of the variances. And obviously, well, let me just verify this. So here we want to verify this. We did this actually, so I don't know why it's in the notes again, but since it's there, we should go through it. Okay, so by definition, the probability that a random variable which is f distributed on n1 minus 1 and n2 minus 1 degrees of freedom is bigger than this thing is exactly 1 minus alpha over 2. So this is the definition of these f values. Okay, so now if I just rearrange this equation, I do divide both sides by 1 over. Obviously this right hand side is never going to change. I'm just manipulating what's inside the probability statement. So obviously the probability of this event is equivalent to this event. Okay, right, so then basically now what do we know? Well, we know the distribution of this random variable is exactly the same as this distribution. Right, so this quantile value hasn't changed, you see this, but remember if you check that basically the distribution of 1 over this is the same as this. You can check chapter 5. Okay, if you don't believe me, let's do it. Where is chapter 5? So the f distribution was pretty much at the end, and this is remember these are the quantiles actually. This is the theorem that I'm talking about. Okay, so if you're wondering what it is, how you could go from this line to this line, it's just an application of the theorem 5.7. Okay, very good. So this is where we've got to. Okay, then the next line, but this is by definition equal to this, right? So by definition, the probability that I'm less than this thing is equal to this thing. Okay, so the point is what? That this value here, it must be equal to this value here. Okay, and this is what this thing is. It's just a restatement. So here you take this one is equal to 1 over this thing is equivalent to doing the reciprocal of that relationship. Okay, so that's where you get that thing. And to be honest, I think that's, as I said, that's here, right? This is what we're saying. This is theorem 5.8 actually. So I don't know. We didn't prove it apparently, but anyway, that's where you get it from. Okay, so a remark, well, it's an obvious remark. If you want the confidence interval for the ratio of the standard deviations, you can just square root both sides of this confidence interval. Okay, I mean this is what the remark is. It's nothing more than that. Okay, this thing follows this confidence interval is a direct corollary of precisely this statement because you can take square roots of everything. It's a monotonic transformation. Okay, so that's that. So let's have a look at a quick example how you can use this formula. Not that you need it, but anyway, let's look at it. So example number 2, we looked at example 1 last week. You have a standardized placement test in mathematics was given to 25 boys and 16 girls. The boys made an average or obtained an average of 82, presumably out of 100, and they had a standard deviation of 8. The girls apparently had this average of 78, standard deviation of 7. So again, a very sexist example. So we're asked to find a 98% confidence interval for the ratio of the variances and the ratio of the standard deviations. Okay. Okay. And we're assuming basically the population to be normally distributed with unknown means and variances. I.e., all we're doing is we're just going to compute this formula and this one. Okay, these two. But that's it. There's nothing else to do. Okay, so what we're told, so sample 1 has size 25 and standard deviation 8. Sample 2 has sample size 16 and standard deviation 7. And we're told that alpha is at, so we're a 98% confidence interval. Okay, so this is basically for this interpolation technique, which I refuse to cover, but you can get this, you could get this from tables if you had the table values. So these f values are needed because you need these f values here. Okay. Okay, and now you're just substituting into the formula. So for example, this one here, just doing it here, this was s1 squared over s2 squared, so s1 was 25 or 5, I forget which one it was. S1 was 8, S2 is 7, so this is 64 over 49. This is my F value here, 64 over 49, this is my F value here. And that's my confidence interval for sigma 1 squared over sigma 2 squared, and the standard deviation is obviously the square root of that. And I think that's pretty straightforward. Okay, so that finishes off basically what was the discussion that we had last week. This now we're moving on to this last chapter, which are hypothesis tests. And actually, the material in this chapter is very repetitive, conditional on doing chapter 6, which obviously is what we have just done, because the idea of constructing hypothesis tests is the following: is basically it's an inversion of all of the confidence intervals we've used. So basically constructing the construction of test statistics to verify hypotheses associated to population parameters are intrinsically based upon confidence intervals in this particular approach. There are other ways of doing it actually, but these are beyond the scope of this particular course. So essentially the point is this: if one understands chapter 6, chapter 7 is essentially almost the same thing, and as you will see as we go through today's exposition. Okay, so basically that information that I just told you is just essentially going to basically be featured in this latter part here, right? Where basically that's the only kind of that's the similarity. The changes are at the beginning of this chapter, where basically we formally define, or up to some minor technical limitations, the notion of a hypothesis test. And basically we think about contributions, I mean, at a really basic level of the notion of type 1 and type 2 errors and the level of significance. And then we're going to construct some hypothesis testing for the mean parameters, and then an alternative way to basically testing, which is based on something called p-values, and then essentially hypothesis testing associated to the scenarios which we looked at the end of chapter 6. Okay, so the notion, the underlying idea is what you want to do. You have the same sitting. You have a random sample of a population. Okay, a collection of IID random variables associated with the population of which you realize. And basically we want to work out whether or not some particular parameter values are plausible, or to work out whether or not some specified idea is consistent with the observed data. Okay? So basically the statistical hypothesis is an assertion or conjecture concerning one or more populations, and obviously we'll start with one population and then move on to two. Okay, and this is not important to say that. So the idea is what we're trying to do. So we're basically going to construct a kind of underlying notion of something that we really want to reject. Okay, so we want to test the notion that is the mean of the population equal to some pre-specified value of significance versus the alternative that is not equal to that. So the idea is that what we want to do is to construct an underlying null hypothesis which we are likely to reject, but at the same time has some significance associated to the problem which we're actually studying. Okay, and then the idea is that basically what we would like to do essentially is to conclude that it's false. Okay, right? So this is the thing. So we're going to have a hypothesis, we're going to accept or reject that hypothesis, and we want to construct this hypothesis in such a way that rejecting the hypothesis is fairly likely a priori. Okay? So acceptance of the hypothesis does not really mean that this is true, but we just can't reject it. It may mean that in fact the underlying hypothesis which we pose is actually not very well specified. Okay, so this is basically a summary, or basically that's the point there. Okay, so the idea is this: you construct an underlying null hypothesis which is hopefully going to be wrong in some sense. So this is the notion H0. Okay, so hypothesis 0 is the null. The null hypothesis concerns essentially a population parameter. Is mu equal to 0? Is mu equal to 10? Is mu equal to 50? And basically, it need not be the case, but in this course, the null hypothesis is such that we're considering whether or not a parameter is even equal to a pre-specified value. It's not necessarily the way to construct hypothesis testing, but apparently we're not allowed to tell you the actual way you do it. Anyway, it doesn't matter too much. So the alternative hypothesis is essentially the complement, if you like. So if I'm testing, for example, that mu is equal to mu 0, a pre-specified value, the alternative hypothesis is often that mu is not equal to mu 0. But it may not always be that way, so there are possibility of several possible values. So we could have the null hypothesis that mu is equal to mu 0, and the alternative that is not equal to mu 0, or the alternative that mu is bigger than mu 0, that mu is less than mu 0, for instance. Okay, and if you're getting confused, this will become very clear in a few moments. So let's have a look. An example is a good time. So in this example, we want to test whether the mean IQ of some pupils at a certain school is different from 100. Okay, so the idea is I want to test that whether the mu, the mean in this context, is equal to 100 versus the alternative. So H1 is the notation, I don't know if I said that before, yes, H1, sorry, is the notation for the alternative. Okay, so this is a hypothesis which we may be, basically is maybe fairly unlikely. Okay, and really we want to reject it from the beginning. And this particular type of scenario that we want to test is something called a two-sided test. Two-sided to two-tailed, I prefer the phrase two-sided. So basically we may like to test, alternatively, instead of having this particular hypothesis test, we may want to do something else. We want to test the mean IQ is greater than 100 or less than 100. So for example, we could test this one. This is a particular hypothesis test. This is another one. And this is yet another one, okay? And these are three different scenarios, and these are one-sided or one-tail tests. I prefer one-sided, okay? So let's have a look. This is basically it's a nice diagram. So the idea is, the claim is that the population mean age, I don't know why it says mean age. Well, let's just say this is a different example which apparently haven't been given. But so we want to claim, for example, let's claim that you have some individuals that the mean age is 50. So that's our null hypothesis. Okay, so we have a population, let's say the population of Singapore, and the null hypothesis is the average age is 50, which is a little bit unreasonable at this moment. Now what you do is of course, we select our random sample, so we have an IID sequence of random variables associated with the population, and we realize that sample, i.e. we get some data. And so now what we do is we obtain the mean of the data. So suppose we take these individuals, let's say there are 5 million people here, and we took 100,000, and the mean sample was, mean age was 20. Now the key point is, now what we want to construct is a decision rule that on the basis of the data, okay, whether or not basically this hypothesis is reasonable, okay. So in this situation we got a mean of the data which is 20, so you probably think that our null hypothesis that the average age of individuals in Singapore is 20 is pretty unreasonable. Okay, and so it's not likely. What that means is, of course, going to be quantified by a probability statement associated to a test statistic associated to the mean. Then we will be able to reject or not the null hypothesis. Okay, now when can you reject this null hypothesis? Well, as I say, so the idea, like I've said, is you construct a functional t, which is a function of x bar and a function of mu. Okay, such that I know the distribution of the statistic. Okay, and then basically on the basis of the realized value of the statistic, I want to work out whether or not the null hypothesis is reasonable. So in this situation, so here he writes the sampling distribution of x bar, but more generally it's the sampling distribution of the associated statistic. And basically, if the null hypothesis is true, and then let's suppose that this distribution is actually Gaussian, then we would have a distribution like that. And we're trying to work out whether or not the statistic which we actually observe is consistent with this distribution. So in our example, if this is really the distribution of our test statistic, and we obtain a value of 20, well, that's basically lying very far in the tail of this sampling distribution of the associated test statistic, which tells us that actually, most likely, that this is not a reasonable distribution for the mean of the sample, and so we would probably reject the null hypothesis. However, if we've got a value of our a statistic which lies very close to this mode, i.e. the mean of the random variable in this example if it's Gaussian, then probably we're going to accept the null hypothesis. But that basically means that essentially it's not a very strong thing to think about. Okay, so the key point is the following, is that what we're going to do, there is a theory in which you can construct hypothesis tests and hypothesis test in an optimal way. Unfortunately, we do not study that, but at least I'm allowed to tell you what the errors are. So there are some sorts of errors, right? So let's suppose we have this, look at this table. So the state of nature, what this tells you is that indeed the null hypothesis is true, or indeed the null hypothesis is false. It's either true or false. I mean, there's no in between. Okay. Now we get what we're going to do essentially in hypothesis testing. What it is, it's a decision procedure where I either accept the null hypothesis or I reject it. Now, if I reject the null hypothesis, okay, but the true state of nature is that the null hypothesis is true, then I have made an error, and this type of error is called a type 1 error. So this type 1 error is basically rejecting the null hypothesis given that the null hypothesis is true. Okay, and in fact that's going to be related to something called the size. So we're going to call this parameter alpha the size, and we'll define that in a moment. The other scenario where you make an error is you do not reject the null hypothesis, but actually the null hypothesis is false. Okay, and this is called a type 2 error, and associated with the type 2 error is this parameter beta, which we're going to define in a moment, associated with the probability that you do not reject the null hypothesis given that the null hypothesis is false. So those are the two types of error that you get in this procedure. And of course what you want to do is, if you define these alpha and beta like this, you'd like alpha and beta to be simultaneously very small. But if actually, so this is called the power, and this is called the size, or no, this is called the size, and this is called the power. And you want tests which have low values of alpha and beta respectively. And in fact, it turns out it's not very easy to do that simultaneously. Okay, these two corners are when you get things right, so they're kind of good. So we want basically alpha and beta to be small, and hence 1 minus beta and 1 minus alpha to be large. Okay, so the type 1 error, so as we said, is the rejection of the null when the null is true, and it's called a type 1 error. And it's considered very serious, right? Because basically you know, your null hypothesis, is, which in our world is the test that the parameter is equal to a point, and you've rejected it. Okay, so you really got some real problem there. And that's supposed to be the most serious of these two errors. And the second one is you reject the null hypothesis. Sorry, you accept the null hypothesis when you do not reject the null hypothesis when H0 is false, and that's a type 2 error. It's less serious, apparently. Okay, so now returning to that table, remember we had alpha, and alpha is defined to be the probability of a type 1, is the probability of a type 1 error. And the type 1 error is the probability that you reject the null hypothesis when H0 is true. That is to say that the probability that you reject H0 given H0 is true. Okay, and generally you set alpha yourself, right? You set alpha to be small because you want to basically make it the chance of a type 1 error small. And then you'd like to make the procedure normally is what it is you set alpha, and then you try to find the test with the smallest possible beta. They're called uniformly most powerful tests, but we don't study that. Okay, so what we're going to do is we're going to set the chance of a type 1 error. Okay, and then basically hopefully our beta is going to be small as well, because remember the beta is the chance of the type 2 error, which is the chance that you don't reject the null hypothesis when it's indeed false. That is the probability that you do not reject the null hypothesis given H1, which basically means H0 is false. And so 1 minus beta is called the power, of course, and so we want tests with large power. Okay, that's what I said before. Unfortunately, this exposition is not very exciting because we don't really use these concepts too much from here on in. But the notion is like this. So basically, you're testing these two null hypotheses. The null hypothesis that your parameter value mu is equal to mu0 versus the alternative that is equal to another value. Okay. So if you know H0 is in the case where H0 is true, okay, this is the distribution the statistic, okay, as a function of the data. Okay, and so basically, so then the type 1 error, which is the probability that you reject H naught given H naught, alpha, okay, then basically you're going to accept, you're going to not reject with this probability, okay, and in this case when H naught is false, i.e. H1 is true, then basically in this region, this is the chance that you reject the H0, which is the size of the test. I'm not sure that really helps you very much, but anyway. So the basic notion is, so that again, like we say, what you want is tests with low size and high power. Okay, and then you set the size and you try to make the test have low power, but that doesn't help us too much for what we're going to do next, which is essentially the following, which is to determine basically how you accept or reject these null hypotheses. So to test a hypothesis about a population parameter, you select a suitable test statistic for the parameter under the hypothesis. Okay, so what does that mean? Well, what that means is, I'm going to try to find a situation where he's written something down which is useful. He has not. So for example, basically what you do, so in this situation, let's say you have a normal population and you want to test the null hypothesis that mu is equal to 100. What you do is you construct a function of the data and of the unknown parameter mu, for which you know the sampling distribution of that function. Okay, and we know loads of those already because we've just done a course on a chapter on confidence intervals. Okay, so that's the first step. Okay, as you can see and as you can see, this phrase suitable test statistic is open for debate. There is lots of things you can do given that you understand the underlying distribution of the associated random sample. Okay, there are many test statistics one can construct, and some are better than the others, as you can tell. Okay, for us, we're going to construct test statistics, and we're not going to study whether they're good or bad test statistics. Okay. So now once you have this test statistic, you then determine the significance level, alpha. That is to say, you determine alpha, which is the probability of this type 1 error. And normally you choose alpha to be quite small, 0.01, 0.05. Okay? Then you construct a decision rule which basically divides the set of all possible values of the test statistic into two regions. So one region is where you reject, which is called the critical region, and the other region is where you accept. Okay. Now, let's try and understand what that is. We're going to see this, how this is obtained. So you obtain a sample, and you obtain the value of the test statistic. And then basically, if the test statistic assumes a value which lies inside the rejection region, then you reject the null hypothesis, and otherwise you do not reject, i.e. you accept. And the values that separate the rejection and acceptance region is called the critical value. Now, all these things will be defined in a moment. Well, you'll see what it means in a moment. So let's have a look at what it means. So let's have a look at an example. So here at the top, what you're doing is you're testing this two-sided test. So you test H naught, that the mean of this data, the mean of this population, is 3 versus the alternative. Okay, so basically then what you do is you determine the distribution of the associated statistic which you construct, which for now is left arbitrary. So in this case they're supposed to be Gaussian. Okay, and then basically, and this is the distribution of the test statistic, assuming the null hypothesis is true. Okay, and then basically the chance that you get a type 1 error here is alpha, because basically these are the extreme values of the distribution, of the sampling distribution of the statistic. Now, in a scenario where basically you have one-sided alternative, so you're testing that mu is equal to 3 versus the alternative is bigger than 3, then you want to test whether or not you lie in this area. So now here you've got one-sided, and this critical value, these are the critical values, so here you have two critical values, here you have one, is basically associated to the chance that you get things, the rejection region here is exactly alpha. And similarly, when you do the alternative is less than 3, then it goes to the lower tail. This, again, is not very evident, actually, without actually defining a statistic. It's not obvious what we're talking about. But I think things will become clear in this following example. So you look at this example, so let's have a look. So we have a type of cold vaccine, and basically a quarter of the time it's effective in over 2 years, okay? And now we want to work out whether or not we should use a better but more expensive vaccine, okay? So what do you do? So what we do is we take 20 people, we give them this new vaccine, and basically we say the following: if more than 8 of those receiving the new vaccine get through the 2-year period without the virus, we're happy. Otherwise, we basically are not, and we just keep on doing the same thing. Okay? So the way in which we construct this, so the way in which we're going to model this procedure is basically we have a sequence of independent and identically distributed Bernoulli trials with success probability P, and P is the chance that you inoculate correctly. Okay, so this is basically, so here P is 0.25 basically. Okay, so basically we want to test the following. We want to test whether for this new sample of data, whether its success probability is a quarter versus the alternative that is bigger. Now, why do we want to do that? Well, basically because if you get if the probability of success of inoculation is a quarter, then you're essentially the same as before. So why introduce this new vaccine? But if it's bigger than a quarter, then you're doing something right, and probably it's a good thing to go forward with. Now, this particular test has been specified from the beginning because we are told precisely that if we get 9 or more individuals that are inoculated, then we're happy, i.e. we're going to accept this null hypothesis, we're going to reject the null hypothesis, and otherwise we're going to be saying that this new treatment is basically the same as it was before. Okay. So the rejection region in this case is the collection of values 9, 10 up to 20, and the acceptance region is when you only, at most 8 people are okay, do not contract. So the decision rule has a level of significance, and we can determine this. So we can, in this particular scenario, we know the acceptance region. So remember that alpha is basically the probability of this type 1 error, which is the chance that you reject the null hypothesis given the null hypothesis is true. What that means is the probability that you reject the null hypothesis is when you get 9, 10, 11 up to 20. Okay, so the probability x is bigger than 8. Given the null hypothesis is true, which is that p is equal to a quarter. So we can compute this really, because this is just a sum from I is 9 to 20 of this binomial. This is a binomial probability mass function with success probability 1 over 4. Okay, so if you compute the sum rather tediously, you'll get 0.04. So in this particular example, this decision rule has relatively low or quite low type 1 error or size. The size of the test is small, which is good. Now, if we look at the other scenario, which is the chance of a type 2 error, which we denoted beta, we want that to be small. Now, in this situation, remember that beta is defined as follows. It's the chance that we don't reject the null hypothesis given that the alternative is true. Okay, but in this situation, remember that the alternative hypothesis is that the probability is bigger than a quarter. Okay, so there are a myriad or many values, or there are infinitely many values which are contained in the null hypothesis. So it's in fact almost impossible to compute beta. Okay, so we consider an alternative test. So let's have a look at the case. We're testing h0 that p is equal to a quarter versus h1 that p is equal to half. And so, of course, in this situation, if we reject this, basically, i.e. accepting this one, we're going to say that we're happy to, of course, obtain or use this new vaccine. Okay, that's why it says a half is bigger than a quarter. Okay, so now we know that the type 2 error is the probability of the type 2 error is the probability of accepting the null given that alternative is true. So we accept when we have that x is less than or equal to 8, and the null hypothesis being false is when p is equal to a half. Okay, and so this is then just the sum i's 0 to 8 of this binomial distribution when p is equal to a half. Okay, and so that happens to be equal to 0.2517. So in this particular test, remember that the type 1 error is still 0.0409 or whatever it was, whereas this one is the type 2 error is relatively small, 0.2517. So basically this looks like a reasonable testing procedure, but of course, like I say, in general, what you do is you choose alpha and you hope the best in beta in general, actually. Okay. So now what we're going to do is essentially just a kind of collection of different hypothesis tests which concern the mean of a population, and basically that's going to be the case. We're going to look at the mean, the variance, ratio of variances, basically anything we could construct a confidence interval for, we're going to construct a hypothesis for. Okay. So we can take the following situation. We're looking at hypothesis testing for a mean, and we have a random sample with a known variance. Okay, so it's a normal but Gaussian sample, actually. So we know the variance, unlikely, and the sampling distributions are either Gaussian or we have a large sample size. Okay, and so this says refer to 6.3.1. So what's the point here? So if you remember 6.3.1, we'll try and find that. It's probably around page 30. So where are we? I can't find it. It's here. So this was the idea. This is the case. So you were constructing a confidence interval for a mean where the population is normal or approximately normal. So we know that the mean is basically Gaussian. The mean of the data, when considered as a random variable, is normally distributed with mean mu and variance sigma squared over n. That's something we verified. And so we know that if this is the case, then x bar minus mu over sigma over root n is basically normal 0.1. Okay, this is just standardization. And this is going to be our test statistics. And we're essentially going to basically, instead of using this pivot for constructing a confidence interval, we're going to use this pivot to construct a hypothesis test. Okay? So we consider basically the problem essentially, so that's the situation that we have. Okay, so let's have a look. So we're going to look at a variety of different hypothesis tests. The first one is we're going to construct a null hypothesis, which is that mu is equal to mu 0, against the alternative that we're not equal to mu 0. Okay, so just as so we know, as I said just a moment ago, as we said last week, that the mean is basically the mean of the data when considered as a random variable is normally distributed in mu sigma squared over n. So under the null hypothesis, right, so assuming the null hypothesis is true, this is basically equal, this is distributed as normally with mean mu 0 and sigma squared n. So what we're doing is we're going to now construct a test of size alpha. Okay, that's what we're doing. So now basically by using this significance level alpha, it's possible to find two critical values, x1 bar and x2 bar, such that if x bar lies between these two values, then we accept, and otherwise we reject. Okay, that's going to be the idea here. That is the idea that we constructed based on the basis of our test statistic. We find these two values, little x1 bar and little x2 bar, such that the probability that we exceed this value is alpha over 2, and the probability that we exceed this value, less than this value is alpha over 2, and the probability to exceed this value is alpha over 2. So the test is going to be of size alpha. Okay, and let's try and do this a bit more formally. So the key point is, how do we find these critical values? So that's based upon the sampling distribution of the statistic. So remember that we have, under the null hypothesis, that the mean of the data is Gaussian distributed with mean mu 0 and variance sigma squared over n. So that means, of course, that x bar minus mu 0 over sigma over root n is normal 0.1. Okay. And so now what we're going to do is we're going to find the critical regions of this statistic for which we will accept or reject, such that the test of the size of the statistic is exactly alpha. Okay, so we'll do that and then we'll have our break. So that is to say, so we know under the null hypothesis, so conditional on the hypothesis being true, null hypothesis being true, that the probability that this statistic lies in this region is exactly 1 minus alpha. Why is that? Because basically this is normal 0, 1, and these are the quantiles of the Gaussian distribution, where the probability that you exceed this is alpha over 2, and the probability you're less than this is alpha over 2. Okay, so then basically the probability that you're between these values is 1 minus alpha. Okay, now remember what we were doing when we were constructing confidence intervals is now we would essentially rearrange this equation for mu, right? And so the probability that mu lies in this region is equal to 1 minus alpha. But here what we want to do is we actually have a different pivot because we're making now statements. We want to find the values of x bar, right, for which if we're bigger than x1 bar we accept, and if we're less than x2 bar we accept. Okay, so if you rearrange this equation, so you add mu naught to both sides of this and you multiply by sigma over root n, then the probability that x bar, which is truly a random variable, lying in this interval is exactly 1 minus alpha. That is to say, if x bar is bigger than this, we reject. If x bar is less than this, we reject, and otherwise we accept. Okay, and the test, the probability of the type 1 error in this scenario is exactly alpha. Okay, and we'll discuss how you can do this test more formally after our break. So we will have a break for 5 minutes, and we'll resume at 14:51. Okay, let's resume. So the idea was, remember, we were just talking about it, but the thing was that basically we would accept or reject this null hypothesis on the basis of these critical values. But in fact, generally what we do, instead of working with directly with the x bar or a statistic, is we work with the function of the test statistic, which makes a little bit more sense. So that is to say, remember that as we say, if x bar lies in this region, little x1 bar, little x2 bar, we accept, and otherwise we reject. But basically the thing is, we know that that's equivalent to saying that this test statistic capital Z lies in Z alpha 2 over 2 minus Z alpha 2 over 2. Okay, so we rather basically work with the statistic directly than perhaps this summary of the data. That's precisely what we do. So let's have a look at an example. So there's going to be a lot of examples in this part of the notes. So you have a director of a factory, and they want to determine if a new machine A produces cloths with a breaking strength of 35 kilograms. It wants to determine if machine A is producing cloths with a breaking stress of 35 kilograms. And we know that the standard deviation of machine A is apparently 1.5 in its production of cloths. Now we take 49 pieces of cloths, and we get the sample mean is 34.5, and we want to ask whether or not is there evidence that the machine is meeting the specifications for the mean breaking strength or not. So we're going to use a test of size 0.05 is the size. So we set that mu is equal to the mean of the breaking strength of this manufacturing machine A. Well, I might call it A actually, doesn't make sense. So what we want to test is whether mu is 35 versus it's not. The reason we want to test that is he or she asks the question, is there evidence that it's not meeting the specifications? The specification is he wants to have 35 and we want to have 1.5, and we're assuming 1.5 is correct. Okay, so that's why we have this particular scenario for our hypothesis test. Okay, so that's the first step. The second step, well, we know the level of significance is told to us, so that's not a problem. So now we know sigma, so we're going to work with the test statistic just as we had before, that x bar minus mu 0. Mu 0 is the hypothesized value under the null, over sigma over root 10, and sigma is equal to 1.96. So because we're using a significance level of 5%, we work with Z of alpha over 2, so that's Z of 0.025, and you can check from the table that's 1.96. So now the critical region is defined by the critical values, which are plus or minus 1.96. So if this statistic, which we realize exceeds this or is below this, we're going to reject, and otherwise we accept. Okay, so now we compute the statistic. That's not particularly very hard. That's 34.5. That's the value of the mean. 35 is the hypothesis value under the null, divided by sigma over root 10, is apparently minus 2.33. Okay, so in this particular scenario, what we have is a value of the statistic which is less than this critical value, minus 1.96. So what we do is we basically reject. So it lies inside the rejection region or critical region, and so we basically accept the null hypothesis that basically 35 is basically being kept up to standard. So basically we're not hitting the standard that this person or director wants to do. Okay, so now this is making a bit more sense. So this graph here, what you see in the red, that red is the distribution of the test statistic, which is standard normal 0.1. Okay, so these are our critical values, minus 1.96 and plus 1.96, and we're rejecting if we lie in these two regions. Okay, so what we observed of our test statistic was minus 2.3 roughly. Okay, which is somewhere about here. Okay, so basically we're rejecting because essentially the realized value of the statistic is highly inconsistent with the associated distribution of the null of the statistic under the null hypothesis. Okay, and so as we said, and as I said, basically we said that this is very similar to the relationship between this two-sided test and the confidence interval. Okay. So remember that the two-sided test is equivalent is very similar to the 101 minus alpha percentage confidence interval for mu. So basically we accept the null hypothesis in this scenario if the confidence interval covers mu0. And if the confidence interval does not cover mu0, we reject. Okay. So that's why, well, basically remember that the probability now that the statistic, that for the same statistic, that mu lies in this interval is 1 minus alpha, which is precisely the same as the probability that x bar lies in this interval. Okay? This is just this computation here. Okay, this is just this computation here. This is the key point, is that the test statistic is related exactly to the pivot of the associated the pivot in either way the test statistic is exactly the pivot that you use to construct the confidence interval, which is why you have this duality. Okay, so if we consider our example, remember that we have x bar is 34.5, sigma is 1.5, n is 49, so there's 95% confidence interval is this one, right? 34.08, 34.92. Our hypothesized value of our statistic, of our parameter, does not lie in this interval, so you can reject. But the key point is basically the test statistic and then the confidence interval are based on the same pivot or statistic, so that's why you have this duality. Okay, so before we continue, so we're going to do a lot more hypothesis tests, some today, some not. And basically there's another way in which you can have a decision rule for constructing tests for associated to hypothesis tests. So the procedure will be very similar. We're going to construct a statistic of the data and the parameter, work out the sampling distribution of that statistic under the null hypothesis such that the size of the test is alpha. But we may use a different way to accept or reject the null hypothesis, and this is called through the notion of the p-value, and that's the probability of obtaining a test statistic which is more extreme, and extremity depends upon your underlying null and alternative hypothesis, than what you've actually observed, given the null hypothesis is true, and it's called the observed level of significance. Okay, and we will see how to compute that in a moment. So how does it work? So the idea is what you do, you construct your sample statistic to a test statistic, just as we did before. You obtain the p-value. How you do that is going to be dependent on the associated distribution of the test statistic, and you compare the p-value to your level of significance. And if your p-value is less than alpha, you reject, and if it's bigger than alpha, you don't reject. Okay, and the question, of course, the key point is how you obtain this p-value, and we're going to see that in an example. So if we return to our example, we had 49 individuals, 1.5 was the standard deviation, 34.5 was the sample mean. Okay. So remember that basically what we did is we converted from the mean to a z-score, i.e. the test statistic was minus 2.33. Now what we want to do, we want to compute the p-value. Now the p-value is what? So the p-value in this context, so we have to compute these two probabilities. The probability that a Gaussian normal 1, which is the distribution of the test statistic under the null hypothesis, is less than the realized value or bigger than the realized value. Okay, so these two numbers you can get from so basically remember that the definition of the p-value, the probability of obtaining a test statistic more extreme than the observed sample. Okay, so in this situation we observe minus 2.33. Under the null hypothesis, z, the random variable, is normal 0.1, so the probability of less than minus 2.33 can be obtained from a table, and the probability I'm bigger than this, well, this is huge. Okay, so the p-value is defined to be, in this case, the minimum of these two numbers, which obviously is this one, multiplied by 2. Okay, so this is how you compute it. In this case, we have a two-sided test. In the one-sided test, it's a bit different, but we're considering a two-sided test. Okay, so in this case, our p-value is 0.0198, but our level of significance was 0.05, or alpha over 2 is 0.025. So we're basically in a situation where the p-value is less than alpha. So we're going to reject the null hypothesis. Okay, so as it says here, you compare the p-value with alpha. If the p-value is less than alpha, you reject, and if it's bigger than alpha, you don't reject. Okay, so here we've got 0.0198, Okay, alpha is 0.05. Obviously, this one is less than this one, so we reject the null hypothesis. So it's just an alternative procedure. Of course, the key point is that you have to obtain these numbers, okay, in order to obtain the p-value, which, at least in our case, will not be too bad because we will know the underlying distributions of the sample statistics for which we're doing hypothesis tests. Of course, that was for a two-sided test. Okay, so let's look at the case where we have a one-sided test. Okay, so it's the same situation. We have an IID sample, a random sample, got normal 0.1 with a known variance, and all we want to do is we want to test this hypothesis that mu is equal to mu0, that's our null, versus our alternative where now mu is bigger than mu0. So in this situation, it's slightly different because basically our alternative will mean that there's a rejection region which is now slightly different. So we look at our test statistic under the null hypothesis, and this thing again is normal 0.1 because basically in the null hypothesis x bar is normal mu0 with variance sigma squared over n. So in this situation, what we're going to do is we're going to reject the null hypothesis if basically this thing is a little bit extreme when associated to the distribution of a normal 0.1. Okay, but in this case, we really only want to look at the upper value, right? So basically, the size of the test is going to be alpha, so this rejection region is now just this upper tail. And similarly, if we go the other way, it will be the lower tail. Okay, so basically, this is a little bit different. So if you go the other way around, this is identical. So this slide is almost identical. It's only this thing that changes. Okay. So this one was Z alpha. This is minus Z alpha. And the probability being to the left of it is alpha. So this is now our rejection region. Okay. So basically, if we get a test Z value which is out here, it doesn't matter. We still accept. Okay. So let's look at a second example. This is essentially looking at a case of a one-sided test in the scenario where we have a Gaussian. So if a manufacturer of a sports equipment, they've developed a new synthetic fishing line that claims to have a mean braking strength better than the market average, which is 8. We want to test, we have the braking test of this, and we know the standard deviation of this thing is 0.5 kilograms, and we take 50 samples, and we have a mean of 8.2, and we want to test the manufacturer's claim where alpha is 0.01. Okay, so this is a one-sided test scenario because we want to test the null that we're equal to 8 versus the alternative that we're bigger than 8, right? Because we want to work the key point here is you want to the key word is better. Right, so we think it's better. So you want to test the null, we want to reject this, and we really want to accept this. Right, that's what we want. So we have this level of significance is 0.01. Our test statistic is set. We know that's equal to x bar minus 8 over sigma over root 10. Sigma is 0.5. Remember, that's what we're told here. Okay, so there's nothing too difficult here. And basically now our critical region, so we're again in this situation, this is going to be our critical region. So our Z of alpha is going to be Z of alpha is 0.01, right? So basically we want Z of 0.01, which is our value. So Z of 0.01 is 2.3.26. You can get that from the table. So our critical region is when this realized value of the statistic exceeds this. So if it exceeds this, we're going to reject our null. Okay, so we now know that the mean, x bar, well that was 8.2, so we get a value of 8.2 minus 8 over 0.5 over square root of 50 is 2.828. Okay, so if we're using this technique, we're going to lie in this critical region, so we reject. We can also think about the p-value. So the p-value is the probability that you exceed this value, okay, where z here is a normal 0.1 random variable. Okay, so from tables you can basically invert the table to get something like 0.0233 as your p-value. So there's only one number in this case because it's a one-sided alternative. So you don't have 2 times the minimum of 2 numbers in this case. Okay, so this is very small. okay, and this is basically going to be less than our level of significance is 0.01. So on the basis of the hypothesis test, either using critical regions or using p-values, we're going to reject the null hypothesis. And that's exactly this what we say in step 5. So step 5, the observed value is 2.828. It lies beyond 2.326, and so we reject. Or if you use p-values, 0.0023 is less than 0.01, so we reject at the 1% level of significance. Okay, and that's the chance of a type 1 error. Okay, very good. Okay, this is basically if you want, this is the critical value approach. So there's distribution. So the red is the sampling distribution of the test statistic. Okay, and then basically 2.326. That's our level of our Z value at level of significance 1.1%, and our realized test statistic lie out here. So of course we reject. If you use the p-value approach, basically this is the distribution of the test statistic. Okay, this is our critical region. Now, in this situation, basically what we want to do is the probability of exceeding 2.828, the probability of exceeding the realized value, which is a little bit further out the tail. Okay, this is this probability. This is the p-value, but it's much smaller than 0.01. So so because this area here exceeds this area here, we reject on the p-value technique. Okay, so that is to say, so you can forget about this line, it's not very useful, but we know that the probability that our test statistic is bigger than our realized value, so that is the p-value, and this thing can be obtained via the table. Well, this is normal 0.1 random variable. This line is not useful. Okay, so that's the interpretation, the graphical interpretation of the decision rule when using p-values. Okay, so yeah, okay, so let's have a look at another test, and this is a slightly more realistic scenario where you have a random sample. You don't know the variance, but the underlying distribution is normal. Okay, I think this is the only other. We'll look at this hypothesis testing today. I want to leave something for tomorrow, so I think this is the last test of the day. So section 6.3.2. Okay, so this is the confidence intervals. Okay, so we go here. This is this. Okay, so we have this case. So remember, in this case, this statistic was t on n minus 1. I think this is not the one we're using, actually. Yes, it is exactly the one we're using. So basically, in this situation, remember that x bar minus mu over s over re10, which is our pivot for computing a confidence interval for a sample mean for this scenario, where basically you have an unknown, a random sample with an unknown population variance, and either it's normal or very close to normal. And the sample, well, here he says the sample size is small. Okay, so that's basically the situation. It's the same thing. So that statistic we just showed you is the one we're going to use for testing hypotheses for the mean. So let's have a look at the case of a two-sided test. We want to test a null that mu is equal to mu0 versus the alternative that is not equal to mu0. And we consider the statistic, just as we just saw a moment ago, x bar minus mu0 over s over root10, where s is the sample variance. And basically this thing we know is t distributed on n minus 1 degrees of freedom. Okay, so that's, again, I've just shown it, but then one more time. This is t on n minus 1. Okay, under the null hypothesis. So again, to ensure that the associated size of the test is alpha, what we're going to do is we're going to reject the null hypothesis if we are exceeding t on n minus 1 alpha over 2, or being less than t minus t n minus 1 alpha over 2. So remember, it's the t distribution is a symmetric PDF. So then in the scenario where we have a one-sided test, what we do, we test, first of all, the null hypothesis that we're equal to mu0 versus that we exceed mu0, and then we reject if we exceed now tn minus 1 alpha. So remember, we have this alpha value because it's one-sided value, whereas this was alpha over 2. And in the case where we want to test a null that you're mu0 and we're less than, and the alternative mu is less than mu0, then it's minus tn minus 1 over alpha. Okay, that's when we reject. So it's very clear when using this rejection region procedure how to do our hypothesis test. So let's have a look at this example. Yes, we'll just go up to here. I think that will be plenty. It'll give us something to do tomorrow as well. So let's have a look at this example. Example 3. So the average length of time for students to register for summer classes at a certain college has been 50 minutes. A new registration is started. You have 12 individuals, random sample, and you basically get 42 minutes for them and a standard deviation of 11.2. Okay, so we want to test that basically this new system is now less than 50, assuming a significance level of 0.05, and of course everything is going to be Gaussian. We're just basically applying the testing method that we had before. So remember what we want to do, test the hypothesis that population mean is now less than 50. Okay, so our null hypothesis is equal 50 because we really want to reject that, and our alternative is less than 50. So that's the answer. The answer to the question why it's in the answer is in the kind of the question. It's basically this sentence here. Okay, the significance level is 0.05. We're not going to do anything. So it's a one-sided test. So the context that we're in is this one. Okay. Now we construct our test statistic. We know sigma is unknown. So the test statistic is x bar minus mu 0, because mu 0 is the hypothesized value of the null, over s over root n. N is 12, okay, and then basically it doesn't imply that, but we can find the critical values by looking at t on n minus 1 alpha. So n is 12, so this is 11. 0.05 is the level of significance. This is 1.796. But remember what our test is. Our test is less than mu 0, so our critical region is going to be, if we're rejecting, if we're less than minus t of n minus 1 of alpha. So we now calculate minus t 1.796. So if our test statistic is less than this value, we reject. Okay, so now we compute our test statistic. It's not exactly hard. We know x bar, we know s, we know n, so we basically can compute t is minus 2.329, and so that's basically less than this value, so we're going to reject the null hypothesis. If you prefer the p-value, so the p-value is the probability that this statistic under the null hypothesis, which is a t on 11 degrees of freedom, is less than minus 2.329. So this is the test statistic. Okay, so basically you can get from the t table this value 0.0199. So in this case, at the level of significance, which is 0.05, also using the p-value approach, you're going to reduce you're going to reject the null hypothesis. Okay, so the conclusion, just as I said, just to make sure, you get minus 2.329. The critical value you reject when we're less than minus 1.796. We are less than minus 1.76. We reject at the 5% level using the critical region methodology. Or if you prefer the p-value, that's 0.00199, and that's less than 0.05. So again, you reject. It's the same scheme. So the conclusion in both cases is that the true mean is less than 50 minutes. So that means that basically our new method of registering classes is better than the old one. That's the idea. That's the answer. If you think that that is indeed, if why? Oh, okay. This is a typo. Yeah, this should say example 3, not example 2. Okay, so that's basically, because we haven't got very much left, so and I don't see any reason to kind of kill ourselves. Let me just tell you what we're going to do tomorrow, and then we can stop, and then tomorrow we will actually do it. So the rest of this course, so the rest of these lecture notes, what we're going to talk about tomorrow are more hypothesis tests. The next one is going to be differences of two means. So the key point is, if you really want to make sure, if you don't want to read this and wait for the lecture, but you want to know really what we're going to do, well, what you can do is you can have a look at all our hypotheses, our confidence intervals here. So here is a confidence interval for the difference of two means, okay? And if you remember, their confidence interval is based on this statistic, and all we're going to do is we're going to use this test statistic to test hypotheses about the difference in the means. Okay, so that was that. Now, now we're going to look at the case where we're looking at two samples, but we have unknown but equal variances. Okay, and we had this test statistic here with this pooled variance, and we could use this one. Okay, and again, if you look at now the next part of this one here, we were doing confidence intervals for the difference between two means. So we looked at the differences. This thing with the difference of dependent samples. So we're going to do a test statistic on that. And the last thing we're going to do is the ratio of variances, i.e. what we did exactly today. So we're going to use f-tests for ratios of variances. Okay, and that's pretty much it. So what I'm trying to say to you is, you're happy with chapter 6, then you're going to be happy with chapter 7, and we're pretty much halfway through it now. Okay, so that's it for today. The only reason I'm stopping is because I want to give us something to do tomorrow. So we will look at that tomorrow, and then that will be it. And then we'll do some extra work and some exam work, and then we'll be finished for the course. Thanks very much for your attention, and I'll see you tomorrow.